Professor Alladi Prabhakar Endowment faculty members and 24 non-teaching staff members. And signal processing, micro and data engineering, BLS and embedded systems will have a PhD program. Since from institution of the department has been a core brand for research and corporate agencies such as MathWorks India Private Limited. The department have made notable contributions to society on a global and domestic scale, and they are offering their unwavering support, 1 crore rupees worth of research block, and hand over to the department to strengthen the research and training activities of the department. I am happy to share that today's President OUC Alumni Association, Dr. D. Vijay Kumar Garu, and for this event also, there is something like Karta Karma Kriya. With their support, we could be able to schedule this event. The department recently also to build a new classroom complex for our EC department. Work is currently underway and the facility should be operational to EC Alumni Association. With these few words, I would like to extend my welcome to everyone for the 5th Professor Alladi. My gratitude to everyone who accepted the department invitation. Thank you.
A warm welcome to the dignitaries on the dais and invitees, alumni of our. Before starting the lecture, we would like to brief you about the genesis of the. Joined the department in 1964 and served the Osmania University in various capacities. He was a great teacher, administrator, who worked tirelessly to further cause of higher education in India. In his honor, with the guidance of Professor Kumpati S. Narendra, Yale University, under the chairmanship of Professor D.V.R. Vittal, the Department of Electronics and Communication Engineering initiated Professor Alladi Prabhakar Endowment Lecture in 2010. The first lecture was conducted in 2012 by K.S. Narendra, and the second lecture in 2014 by Dr. Peter Perisek, Australia, and the third lecture by Professor N. Viswanathan, IISc Bangalore. Fourth lecture, Dr. Nirmal Saxena, NVIDIA.
Professors who taught us were here in the first row. To the existing learned faculty, fellow alumni, and my dear children. It's actually a great privilege to stand over here today and talk about Professor Bhiksha Raj, and more than anything talk about and reminiscence our interaction with Professor Alladi. I think it's an emotional moment for most of us because, as always, or all throughout our life, we were also not the front benchers. We were those typical, backbenchers who were into everything under the sun. Okay? And everything under the sun, which also includes academics, kind of a thing. Okay, and we were one of those naughty groups that were there. It goes for every batch, but I think we were slightly naughtier than most of the batches. And an ECA department is supposed to be a very strict in terms of discipline, in terms of timeliness, everything. You are different. Your road ke is par. You can't compare yourself with civil or any other department. You are on this side. And we were constantly reminded by our profs. And the most prominent of him is actually not here, but is always here. Professor Pandey sir used to, consistently remind us every week or 10 days or once in a month, saying, you guys are from EC department. Okay, one of the instant that we can recall our interaction with Alladi sir was, as always, Diwali came. This was in second year. and we started bursting crackers inside the department. We started bursting crackers. We brought laddies. Now you have a HOD room, right? You have your third year, and previously in front of the HOD's room, it was third year and fourth year classroom. So we used to come up, take the laddy, light it, throw inside the classroom and run. We did that, and at the end of the corridor, you take a right turn and you run, and from the other stairs, you go out of the building. We ran and turned, and then you saw Professor Alladi with his big tie suit standing like this, and we bumped into him. And he said, yeah, what's happening? You're bursting crackers. We were caught red-handed. Okay, and he was one of the senior most profs then. This I'm talking about in 85. The beauty about it is we were actually scared and shitting. But he immediately took out 20 rupees from his pocket. 20 rupees is a big amount then. He gave us and said, you should not do all this inside the department. Okay, go buy rockets. We will all burn rockets outside the department. And we actually burned rockets in front of the EC auditorium. Okay. Now it's a relationship that continued further. Every year for Diwali, we used to land up at his home in Himatnagar. He used to buy and keep laddies, rockets, all the crackers. As students, every Diwali, religiously we used to go to his home and burn crackers.
Actually, even earlier today, I just got nostalgic and I went back and checked my marks sheets from way back when. I have memories of my marks sheets which are not very nice. And so I just realized that I got some happy news, and I also discovered why I got into research. I've always thought that I was a D student. In all of my recollections, I've never seen 70% marks in any of my courses. I found that I was not a D student, I was a C student. So that was the good news. The second one is the self-discovery. The reason I ended up in research was nobody would employ me with those grades. So it's this is perhaps, a reason for even the worst among you to hope that someday you'll actually end up on this stage doing a talk. Anyway, let me begin. I would like to start off by this stopped working. Paying respects to Professor Alladi Prabhakar. I was one of the last batches, possibly the last batch, to actually sit in a class that was taught by him, and he was a wonderful man. So while he is not here, he remembers a very intimate part of my memories and the memories of all of my classmates because he was such a wonderful man. So it's an honor to be here in an endowment lecture in his name. Second, I have a confession to make, which is that I was not entirely sure of who would constitute the audience for my talk. And I teach students. And so the bulk of my talk is targeted at students and at trying to explain things in a manner that I usually do in my classroom. So if you find this not up to the standards of these great lectures in the past, which are part of the Alladi Prabhakar series, I want to apologize in advance. I'm going to do my best anyway. All right. Third, let me introduce myself. I'm Superman. Only when nobody's looking. So whenever the right call comes out, I jump into a phone booth. I come out looking like that. But at other times, I'm in disguise and I look like this. And when I'm in disguise, I'm Bhiksha Raj. I'm a professor in Carnegie Mellon University in the Language Technologies Institute over there. But then I am also affiliated with a whole bunch of other departments like electrical and computer engineering, machine learning, and music technologies. Amazingly enough, someone somewhere thinks I do music. I'm also a visiting professor in the Mohammed bin Zayed University of AI, which is a somewhat new university meant only for AI that has been set up in Abu Dhabi in the UAE. under the auspices of the Emir himself, Mohammed bin Zayed. My research areas include speech processing, computer audition, machine learning, deep learning, and a whole bunch of associated topics. My talk for today is going to address one very specific component of machine learning. So everyone here, anybody who has not been living in a cave would recognize this slide. ChatGPT has been out there in public for about a year now, but it's been out amongst the researchers for much longer because we've been working with things of this kind. And it can do amazing things. Here's an example of where I asked Bing, is 1993 a prime number? It worked out the math. It knew how to work out the math. Or here is one where I asked it a question to which I didn't expect it to know the answer, which is, what was the motivation of the antagonist in Kayamat Se Kayamat Tak? This is a movie that came out when I was in college, and Bing knew the answer. So you'll be surprised, right? Or I gave it a story from the Jataka Tales, and I asked it the moral of the story, just like that. And it knew the answer. It was a perfectly good answer. Now, this is all, playing with language, playing with words. So I went one step further. I pulled out a little PDF from my assignments, and I asked it for an answer. And it showed me that you guys can cheat. You can just take my exams and pass it to ChatGPT, and it's going to give you the correct answer more often than not. Sometimes it will lie, and if you depend on it too much, then you're going to lose 20% of your marks. But it's right 80% of the times. Now, it's not just a party trick. People have been using these technologies for all sorts of things. So here is a very nice article from the National Library of Medicine, where they are using these large language models for drug discovery and development. In other places, we've been using it for things like predicting war, in the banking industry to help with governance, and in a whole lot of other things. And one of the very shocking discoveries we've made is that eventually it's all language. So maybe the primary root of human intelligence is just our ability to generate language. And maybe and what does this thing learn from? It can also do other things. It can draw a colorful picture of a harlequin drawing in a field on a sunny, beautiful day in a beautiful village. It does that, right? It knows exactly what I mean, and it's able to do or generate these pictures. Or write a poem about a beautiful large moon on a starry autumn night. It gives me a perfectly acceptable poem to answer this question. So where did all of this come from? First, there's a lesson in this for you. ChatGPT learned to do every one of these magical things by reading. It didn't restrict itself to reading textbooks. It didn't restrict itself to reading mathematical articles. It read everything that you threw at it. It read and it read and it read, and it's able to generate what looks like genuine intelligence, which seems to tell me that the secret of being really smart is to read everything and anything you ever can. Not to be restricted, because the more you read, the more you learn. That's what ChatGPT is already telling me. But then let me get on to the mundane portion of my talk. That's my high-level lesson for the day. I'm done. And so how did this AI become so profound? It turns out that it's not really very profound. This kind of AI that we've seen is an emergent phenomenon. It just comes from, like I said, reading or training very large models like your brain, with very large amounts of data. And the actual architectures of these models are very mundane, so mundane that pretty much every one of you can build one of these models on your own if you have the compute resources for it sitting in anyone can do it. There are companies coming up daily on building large language models for all kinds of tasks, but not just large language models, AI in general for all kinds of tasks. And in many of these companies, some of who I have been tracking, some of who have built some of the greatest state-of-art tools, AI tools available out there today that you are probably using knowingly or unknowingly. In each of these cases, the time delay between let's go to here it is about 4 months. That's it, right? So what's the secret? The magic lies in the availability of data, on the availability of compute, but more so in the availability of data. It's again about ingesting data and processing it. Massive amounts of data, and these data must be collected from all available sources. And so this thing is so important that, where does the data come from? It comes from anywhere. And when you say anywhere, imagine going out to the web and scraping every web page that you can think of. What kind of data are you going to get? It's going to be very, very, very messy. If I download a standard data set, standard web page, and I try to find what questions I can answer based on that web page, you won't even be able to find the questions, let alone the answers. And so these data cannot just be presented as is to the AI model to learn the model. They must be curated. And so you end up with a situation where in all of these companies that are building these very large systems, the majority of the expense, once you get past compute, is on data processing. They have a few engineers who can write code, like you could from your living rooms. And then they outsource the data processing to other companies, and they spend tens, if not hundreds of millions of dollars on trying to collect the data, clean it up, process it, and set it up in the right format so that that data can now be used to train the model. And this seems kind of wasteful, right? If I'm sitting in my living room and I want to use compute to actually train, I know how to write a scraper. I can and have written scrapers that can download massive amounts of data from the web. I don't know how to use it because I don't have the pocket that can be used to clean the data up. So the question that I as a researcher ask myself is can I just work directly with this messy data? I don't want to spend the time and effort to clean up the data. I'm going to assume that compute is free. It is not, but my assumption is that compute is kind of free. Or even if it is not free, I can afford it, right? And so I'm going to replace, because human time is much more expensive than compute time every single time. And so let's see what I can do with messy data. So how can data be messed up? Typically, when I'm going to train an AI model, the way I do it is you perform all kinds of tasks. You ask it to write a poem. You ask it to summarize a story. You ask it to sing and dance. But then you have to teach it to do this, which means you give it the question, examples of questions, and examples of the corresponding responses. And then based on these examples of questions and responses, the AI learns to do the right thing. This means that you need these examples, the question and the response. And that's the data you want, and that's the data you are not going to get. That's why you spend money on it. So again, as a researcher, I want to save myself this effort. Can I work with this messy data? And more generally, can I reduce the stringent criteria on data to enable training models? Now, this is about as complex a statement as I'm going to make, because the rest of my explanation is going to be boiled down to really, really toy examples with the hope that they will be simple enough for you to understand, to get the basic concept. And I'm not going to try to generalize out of those, right? So let's go back and look at this example of how data are challenging. I work on audio. One of the problems I want to work on is building systems that can recognize sound events. So you want to have a computer that can just listen to this room and say, here was a dog barking, and then here was a glass shattering, and then here I heard a car screeching away, here someone screamed, here I heard a police siren. You want to be able to identify these events in the sound recording, which means, of course, that you need the system to listen to the recording and tag the occurrence of these sound events. And in order to be able to tag the occurrence of these sound events, it must know what the sound event sounds like, which means it must have a model for the sound event. And so typically, assuming that you have models for all of these sound events, you're going to have a little sliding window, which you keep sliding along the signal. And within each segment, you're going to say, does it have the dog? Does it have the glass? Does it have what have you, right? And so within each of these segments, you have to perform a classification for the classes that you're interested in. So this is a classifier and the classifier must obviously be. Now, how do we train such classifiers? What do we spend money on when we train such classifiers? You get idealized data, which is, I want to train a classifier to recognize dog barking. So I'm going to get myself a lot of little snippets of audio with dog barks, a whole bunch of other snippets of audio without dog barks. And then you can see why this is going to be expensive, because I'm going to have to listen to lots and lots of recordings and say, okay, here's an example of a dog barking. This is not a dog barking, right? It's very expensive. Now, if I just try to grab data from the web directly instead, I would actually either not get data of this kind, or I would have to pay someone to say, here is the portion in the recording where the dog barked. These are portions where no dog barked. And so this is a very laborious and expensive process, and it's also error prone. People will miss segments where dogs were barking. They will mislabel other regions where dogs were not barking. So the question I can ask is, can I just take this recording and say, this recording includes dog barks. This recording doesn't include dog barks. Now, if I go and download data from YouTube, people will annotate this sort of things. They're going to say, here's a recording, my dog barking. It will be maybe a 15-second recording. Somewhere in it, there's a dog bark. And then you're going to have other recordings of something else, and you can expect that there is no dog bark in the recording. The problem here is that, so now our instance of what is positive and what is negative changes. This is a positive instance of a dog bark. This is a negative instance of a dog bark. But the problem is that we don't know where in this entire recording the dog barked. It may have barked just over here, which means all the rest of it, that's actually a negative. A dog was not barking over there. So to give you an idea, I can give you a 30-minute recording and say this is a recording of a gunshot. How long is the gunshot? 5 milliseconds. The recording is 30 minutes. How do you learn a gunshot classifier from a 30-minute recording, which includes just a 5 millisecond? Or let's take a look at images. Typically you'd want to scan an image and say, aha, here are all the objects in the image. This is a globe, this is a staple remover, this is a cat behind a box, right? Now, in order to do this, again, you're going to need models. So which means you're going to need a classifier. If I want to detect staple removers, I'm going to need examples of pictures of staple removers, examples of pictures of other things that are not staple removers but may look like them. And from these, I'm going to try to train my classifier, right? Now, for this again, it means that I'm going to get pictures of this kind and then pay somebody to segment out the staple removers from it. And once again, this is going to be very expensive, right? So segmenting and labeling each individual instance is laborious and very expensive and also error prone. It would be much simpler if I could just say, here's a picture. This picture has staple removers. This picture doesn't. I'm not telling you where the staple remover is in the picture. I'm not telling you how many staple removers there are in the picture. I'm just saying this is a picture with staple removers. This is not. That's the kind of data I can very trivially just go on the web and get. We work with this kind of data all the time. But then, how do you work with such data, right? How do you train a classifier with such data? So let's go back and look at the problem. I'm going to simplify things. I have this 30-minute audio recording, and it may or may not have dog barks. I can begin chopping it up into little 1-second segments. Now the recording that has a dog bark becomes a collection of segments, some of which are dog barks and the rest are not. So it's actually a bag of segments, and in that bag there are some instances of a dog barking. This other recording, which didn't have a dog bark, can similarly be chopped, and now I'm going to have a collection of segments where none of the segments in the collection includes a dog bark. So now I can each recording just became a bag of segments, a bag of instances. And when I say something is a positive bag, it means that the positive bag was obtained from a recording that actually included dog barking. And so somewhere in this bag is an instance of a dog bark. A negative bag, on the other hand, is a collection where there is no there are no dogs barking. And now this is the kind of data that's very easy for me to obtain. I can just download it off the web. Now my problem is trying to train the classifier from such data. So that's what we need to do. Now, generalizing, here's the conventional problem of learning. In the conventional problem of learning, you're given many training instances, where for each training instance, you have a very carefully labeled example saying, this is a staple remover and this is not. Whereas what we will have are collections. And you have positive collections. In the positive collections, you may have one or more instances of your target class. In the negative collections, you're not going to have any instances of the target class. And you're going to have to train classifiers from this. Now, those of you in this class who are awake and who are paying attention, they probably already know the answer. Because once I state the problem in this manner, you can come up with solutions. But for those of you who are not awake, I'm going to hope that you will wake up and follow me. And so I'll give you the solution, right? A bunch of solutions. So here again, we have labels at collection level. And let's look at some common sense solutions, right? I'm going to simplify the problem even further, just for the sake of illustration. So I'm going to try to create a classifier that can recognize instances of the digit 2. So I have a collection of numbers. I've created bags. Some of these bags include the digit 2. Other bags do not include the digit 2. And these are all instances. I actually have actual simulations that I obtained from data drawn from the MNIST corpus. Some details of the corpus are on the slide. Okay. And so for my experiments, I created 50 such bags, positive bags, which have an example of 2 in it, and 50 such bags, negative bags, which don't have a 2 in it. And from this, I'm going to try to build a 2 classifier. I'm not trying to classify bags of 2. I want to be able to look at an individual instance and tell you whether it's the number 2 or not, right? And so these are just details of my data set, okay? The binary experiment we're going to be running, the binary classification experiment, is recognizing the digit 2, but using bags. Now, after building my classifier, what I really want to do is to classify individual instances, not bags. I want to look into the bag and say this, and this are 2, and this is not a 2, right? Okay, but then I can also do another thing. I can look at a bag and say this bag contains a 2, or this bag doesn't contain a 2. So there are 2 different tasks. Which of the 2 do you think is going to be more erroneous? Anybody? And we're also going to find that bag accuracy for positive bags is generally going to be greater than bag accuracy for negative bags, right? Now, let's return to the problem. I'm going to try to run one common sense solution. And the common sense solution is the simplest thing that you would have thought of. I'm going to just say that every instance in my positive bag, since I don't know better, is an instance of the class. So if I have a bag which says this bag has instances of the digit 2, I'm just going to say every instance in this bag is 2. If I have a bag which is a negative bag, and I'm told that there are no instances of 2 in the bag, I'm going to say all of the instances in the bag are not 2. And so that's the simplest case. Now, in the best case, I have strong labels where I have the actual labels for every instance, like I'm showing on the slide. When I have the actual labels for every instance, how well does my classifier perform? This is an easy task. I can classify digits correctly 97.725% of the time, and I can classify bags, entire bags, correctly about 80% of the time, which is a pretty damn good performance, right? But then, this is when I have labels for every instance in the bag, within each bag. Now, if it's a negative bag, then every single instance in the bag is negative. So I can assign a label to every one of them. There's only one way of assigning labels to all the instances in the bag. If it's a positive bag, then I end up with a graph of this kind, which is kind of crazy. It's an ugly looking graph. It's not very clear where the graph came from. But then if I take any path through this graph, it has a characteristic that the sequence of colored nodes on the path gives me one way of labeling all of the data instances in the bag. And it turns out that this graph can always be drawn so that it's not exponentially sized, it's very finite in size. Now, where did this graph come from? Where did this crazy graph come from? Here's a finite state automaton that actually shows the graph. I won't explain it. But basically, once you have a graph of this kind, you can compute an expectation over all possible ways of labeling data over this graph using something called the connectionist temporal classification framework that some of you might have been familiar with if you've taken any deep learning courses. And in finite time, in polynomial time, you can learn your model from very poorly labeled data. So then that sort of brings the problem down to how do you compose this graph? Yes. So let's take a look at it. Let's take a look, right? So when I have data instances arranged in some order, then I can always draw if I have this situation where I say this collection is a positive collection, then it means that there's at least one positive instance in the collection. So I can think of a finite state automaton which goes through a sequence of steps, and at each step it assigns a label to one of the instances in the bag. So then for a positive bag, the finite state automaton ends up looking something very simple. It says that I can stay in the first state so long as the instances are negative. Then the first time I get a positive instance, I go to the second state, and then at the second state I can subsequently label things as either positive or negative. So this is a simple two-state automaton that's going to capture every possible way of labeling a collection of instances in a bag so that the bag has at least one positive instance. Or if I have an information which says that if I have the precise label for all the instances in the bag, I get an automaton which is just a very simple sequence. If I have a bag where I don't tell you whether any of the instances are positive or negative, that gives me a one-state automaton. Suppose I give you information which says that this bag has two positive instances, then that gives me a three-state automaton. If I say the bag has at least two positive instances, then it gives me a three-state automaton. It turns out that regardless of the kind of information you give me, I can draw an exact or approximate automaton which represents the information in the bag. And subsequently, I can draw things. All these are non-deterministic finite state automatons. And so any way of labeling data can be recast as a non-deterministic automaton. And most but not all of them will result in quadratically sized graphs. And if this cannot be done, you can always have factored approximations. And then once you can actually draw a graph of this kind, you can train your model using very well-known algorithms in polynomial time. And so as a result, you end up with a situation where regardless of, we have some results that I'll skip, but in all cases, what we end up is one common algorithm, and all we do is to translate the imprecise information that you have about how the data how a data instance is labeled into some kind of a finite state automaton. And then the finite state automaton leads to polynomially timed training solutions. So this means that suddenly I find myself in a situation where I can train my AI with data that I download from the web. So long as, I'm still going to have to expend money on it. But then when I expend money on labeling the data, the expense is going to be on simply trying to assign the kind of noise the data instance has, as opposed to say, cleaning it up or curating it, throwing away the bad stuff, segmenting stuff out. So the amount of money you'd spend could go down from $100 million to $1 million, yes. Based on this very simple idea, we've actually, we in my research group, we've come up with a whole bunch of solutions. And some time ago, my student Hao actually came up with a unified standard, along with the scientists at Microsoft, came up with what they call a unified standard framework for evaluating models, which have been trained on all kinds of crappy labels. And this is unified SSL benchmark, which anybody can actually download and people are now using on the web. So just to get to the end, I haven't actually gone through a lot of details. I haven't gone through my results because I don't think that's they are very telling for the story itself. The point I was trying to make is that real life conditions exhibit a variety of require large amounts of data to train an AI. The amount of data that you need is so large that you're going to have to get it from a varied number of sources. When you get data from a varied number of sources, then the data are going to have all kinds of imprecisions, approximations, and noise in your labels. And classic solutions don't work. We're going to need a completely new set of solutions if you're going to democratize AI and say somebody sitting in a lab in OU can still train my models without spending several crore rupees on cleaning up my data, just so long as somebody gives me the compute. And for that, the way to do it is to view whatever information we get as information that places constraints on the labels. And once you do so, we have actually come up with a framework that allows you to train all of these models in reasonable time. So this opens up the possibility of training any classifier with any form of data from the wild with all kinds of vagaries of labeling. I'll stop right here because I don't know how else to stop a talk. You just stop abruptly. From the looks of my audience, there will be no questions. But then if there are any, I shall take questions.